Here is another video on radicals. Let's begin with a definition. Two integers are said to be relatively prime if and only if their only common factor is 1. For instance, 6 and 25 are relatively prime, but 6 and 27 are not. 6 and 25 only common factor is 1. Factors of 6 are 1, 2, 3, 6. Factors of 25 are 1, 5, and 25. No common factors other than 1. 6 and 27 are not relatively prime because 6 has 3 as a factor, so does 27. Examples. Determine whether the given pair of integers are relatively prime. 572 and 119. Let's look at 572. Prime factors of 572 are 2. So 572 is 2 times 286. 286 is divisible by 2. Is 2 times 143. 143 is not divisible by 2, but it does happen to be divisible by 11. So 143 is 11 times 13. The best way to realize that 143 is actually divisible by 11 is to realize that 143 is simply 110 plus 33. 110 is divisible by 11, 33 is divisible by 11, so the number 110 plus 33, 143 is divisible by 11. So when you divide 143 by 11, you get 13. Let's look at the 119. 119 happens to be divisible by 7. So 119 is 7 times 17. Best way to see that the 119 is divisible by 7, just realize that 119 is 70 plus 49. So 7 is divisible by 7, 49 is divisible by 7, so their sum is divisible by 7. So 119 is 7 times. When you do the division, it will be 17. As you can see, prime factors of 572 are 2, 11, and 13. Prime factors of 119 are 7 and 17. They have no common factors other than 1. Conclusion, 572 and 119 are relatively prime. Now let's look at 243 and 7,483. 243 is divisible by 3. 243 is divisible by 3. When you do the division, that's 3 times 81. 81 is also divisible by 3. It's 3 times 27. And 27 is divisible by 3. It's 3 times 9. And 9 is divisible by 3. So the only prime factors that 243 have is 3 itself. So 343, prime factors of 243, only 3. So question that you have to answer now is 3 a factor of 7,483? So let's try to find out. So 7,483 divided by 3. That's not an integer. So as it turns out, 3 doesn't divide 7,483. that means that the only common factors between 243 and 7,483 is 1. So those are relatively prime. Okay, let's continue. Now a rule, the rational exponent rule. Let b be a suitable real number and let m and be integers with n greater than 1. The nth root of b to the power m equals b to the power m over n. For instance, the cubic root of 8 squared is the same as 8 to the 2 over 3. Notice that 8 is the same as 2 to the third. So we end up with 2 to the third raised to the 2/3. Now I am raising a power to another power, so I keep my base and multiply my exponents. So it's 2 to the 3 times 2/3. Notice that the 3 and the third cancel each other, so you end up with 2 squared, which is 4. If you want to confirm the rational exponents rule, all you have to do is raise each side to the nth power and confirm that they are the same result. So the right hand side, b to the m over n, when you raise it to the n, gives you b to the product of the exponents, m over n times n. Notice that the n's cancel, so you end up with b to the power m. When you take the left hand side, the nth root of b to the m, and you raise it to the nth power, by definition, that's just b to the m. The nth root of b to the m to the nth power is just b to the m. Notice that they produce the same result. That means that these two are the same number, precluding signs, of course. So b would have to be suitable for this to work. Examples. Simplify the given radical expression. So here I'm going to write the cubic root of 64 squared. I'm going to write that as 64 to the 2/3. So 64 to the 2/3. Now realize that 64 is actually 2 to the 6. 2 to the power 6 is 64. So I'm going to write it that way. Two to the 6. All of that is being raised to the 2/3. Notice that now I apply my 8 rule of exponents, where a power raised to a power, you keep the base, multiply the exponents. The base in this case is 2. The exponents are 6 and 2/3. So I'm multiplying those. 6 times 2/3. There is some simplification here. When you cancel, the 3 cancels. So you get 6 over 3 is the same as 2 over 1. So you end up with the result 2 to the power 2 times 2 over 1, which is 4. And then you know 2 to the 4th is simply 16. Next example, I want to take the 4th root of 400 to the 6th power. The 4th root of 400 to the 6th power. Well, that is the same as 400 to the power 6 over 4. Notice that 6 over 4 can be reduced. So when you reduce 6 over 4, you get 3 halves. Observe that 400 is actually a perfect square. It's 20 squared. And I'm saying that because I see that that square will actually cancel out with the 3 halves. So this is just you planning in advance to simplify the exponents. I could have factored 400 into prime factors, but here writing it as 20 squared does something good for you. It gives you a nice integer exponent. So you get 2 to the 20 to the third power. When you multiply 20 times 20 times 20, you get 8,000. Okay, next, we want to simplify the square root of b to the power 12. Recall that when you have square root, that means the second root. So I'm going to write square root of b to the 12. But I know that that means the second root of b to the 12. Now I use the rational exponents rule, which is nth root of b to the m is b to the m over n. So I get 12 over b to the 12 over 2, which is 6, right? So my final answer is b to the power 6. Last example in this group is simplify cubic root of x to the 6th, y to the 9th. So let's first split this up. I can use my rule that says that the nth root of AB is the nth root of A times the nth root of B. So I'm going to do that right now. So I end up with the cubic root of x to the 6th multiplied by the cubic root of y to the 9th in each of these radicals. Now I get to apply the rational exponents rule. So the cubic root of x to the 6th is simply x to the 6 over 3 times the cubic root of y to the 9th is the same as y to the 9 over 3. That those exponents simplify. 6 thirds becomes 2, so that's x squared. And y to the 9 over 3 is simply y third. So my answer is x squared y cubed. Okay, let's make some remarks. First one, the rational exponents rule implies that for suitable values b, the nth root of b is simply b to the power 1 over n. If m and n are relatively prime integers, the rule b to the power m over n equals nth root of b to the m holds for negative values of b provided n is an odd integer. When m and n are relatively prime integers with n even, adopting that as a rule will lead to inconsistencies. So we do not adopt it in such case. When we study complex numbers, you'll see what the inconsistencies would be. In treating the expression b to the power m over n, where m and n are not relatively prime integers, we first reduce the fraction m over n and then apply the rule, the rational exponents rule. For instance, if you want to calculate negative 8 to the 4 over 12, first deal with the 4 over 12. 4 over 12 reduces to 1/3. So negative 8 to the 4 over 12 is the same as negative 8 to the 1/3. That happens to be the cubic root of negative 8, which is negative 2. Okay, that's all for now. Thank you for watching.